Hi, I'm starting the fourth and last chapter of this course. Chapter 4 is about inverse, exponential, and logarithmic functions. So the first section is on inverse functions. And back to chapter 2. In chapter 2, we learned that a relation is a function if no two values of y correspond to the same value of x. Okay, the y values can repeat. I mean, the x value or two different x values can have the same y value, but not the other way around. So one example of something that was a function was this, or an example of something that is not a function. 1, 0, 1, 1, and 2, 1. This is not a function. Because you have the same x value associated with two different y values. On the other hand, the relation 1, 0, 2, 0, 3, 1 so you can have the same y value matching with two different x values, and that's okay. That's still going to be a function. So that one is a function. Let's say we have, yeah, just keep it like that. You have 1, 2, and 3. They all match with 0, and that one is a function, but it's not going to be a one-to-one function. So before talking about inverse functions, we need the idea of a one-to-one function. And a function f is a one-to-one function if for elements a and b in the domain of f, a not equal to b implies that f of a does not equal to f of b. That is, different values of the domain correspond to different values of the range. So I can show you with examples. This is very similar to the one I did. The relation f equal to 1, 0, 2, 0, and 3, 1. This one is a function. It's a function, but it's not a one-to-one function. You might have different x's corresponding to different y's. So not two x's can correspond with the same y. And the relation 0, 2, 1, negative 1, and 2, 0. Now that relation is a one-to-one function. You have different x and y values. So no y value is repeated. Now let's suppose the equations, the functions are given by equations. We take f of x equal to x squared. That is going to be a function, but it's not one-to-one. It's not one-to-one because you have two y values, in this case, -1 and 1, with the same y value. Or -2 and 2 also have the same y value. So this function is not one-to-one. It is a function, but it's not one-to-one. And I could keep on going. Like -3, you have -3, 9, and 3, 9. Or -4, 16, 4, 16, and so on. And the function f of x equal to x raised to the third power. So let's make a table. You're not going to have the situation that we have with x squared. So every x value corresponds to a unique y value. So you have 1, 1, and you have -1, -1. Or you have 2, 8, and -2, -8. So graphically, you have something called the horizontal line test. That is very similar to the vertical line test. But yeah, some values are okay, so I'm drawing this graph again. And then I'm just going by 2 by 2. Okay, so some points on the graph of the function are -2, -8, -1, 1, 0, 0, 1, 1, and 2, 8. So there's a way to tell from the graph whether a function is a one-to-one function, and that is called the horizontal line test. Remember x squared? I didn't do the graph. Okay, so yeah. So we know this graph well enough. So I'm drawing this graph. Okay. So we have something called the horizontal line test to determine whether a graph represents a function. That's on page 407. It's very similar to the vertical line test. The horizontal line test says that a function is one-to-one if every horizontal line intersects the graph of the function at most once. A couple of examples. So let's say that the graph of the function is something like this. If you use the horizontal line test, you can see that every horizontal line crosses the graph at most once. So this function is one-to-one. And if a horizontal line crosses the graph, if there's a horizontal line that crosses the graph more than once, then the function is not one-to-one. Let's say that this is the graph of a function. And yeah, let's say we have a polynomial function. So that one is not going to be one-to-one. because there are going to be horizontal lines that cross the graph more than once. Doesn't mean that every horizontal line will cross the graph more than once. Like you could have this one that crosses the graph only once. But if there's one horizontal line that crosses the graph more than once, then the function is not one-to-one. Okay, and the reason to talk about one-to-one functions is because in order to talk about inverses, we need to know what is a one-to-one function. So if a function is one-to-one, then it has an inverse. And the inverse is obtained by interchanging the values of the domain and range. So I'm trying to see if there's the definition of the inverse. Yeah, so I'm going to type this. So the notation for an inverse function. So if a function f is one-to-one, then it has an inverse and is denoted by f raised to the negative first power, to the -1. This stands for f inverse. It's not a reciprocal. That's the notation for f inverse. And if f is one-to-one, then its inverse is obtained. So I'm going to write this by hand. Is obtained by interchanging the domain and range of f. Okay, so the inverse is written f inverse. I'm going to bring this. Okay, so the inverse is f inverse. So the inverse is obtained by interchanging the domain and range of f. Examples. We're going to find the inverse of each function that is one-to-one. The first function is going to be a table. Okay, the x values are even non-negative values, 0, 2, 4, 6, 8, and 10. F of 0 is -2, f of 2 is -1, f of 4 is 6, f of 6 is 9, f of 8 is 3, and f of 10 is 7. So the inverse what I'm going to do to write the inverse is just interchange the domain and range, but we're going to write the values in order. So let's write the y values in order. Those are -2, -1, 3, 6, 7, and 9. Okay, so f inverse of 2 is 0. F inverse of -2 is 0. F inverse of -1 is 2. F inverse of 3 is 8. F inverse of 6 is 4. F inverse of 7 is 10. And F inverse of 9 is 6. MB. the function is 3, -1, 2, 1, 0, 2, 1, 3, and -1, 0. So you know that the function is 1-to-1 because no x value is repeated. In a function, no x value is repeated, and in a 1-to-1 function, no y value is repeated either. Okay, so the inverse, what we're going to do is write the y values in order. So if we write them in order, we first have -1, 3. So we are switching the coordinates. The next y value in increasing order is 0. So -1, flip the terms or flip the coordinates, that's -1, 0. Next we have 1, 2. From 2, 1, we obtain 1, 2. From 0, 2, we obtain 2, 0. And from 1, 3, we obtain 3, 1. So that's the inverse. There's a couple of notes. The composition of a function with and its inverse. So the composition of f and f inverse must be equal to x for every x in the domain of the inverse, which happens to be the range of the range of f. And in this particular case, the composition is commutative. F inverse, or the composition of f inverse and f, is equal to x for every x in the domain of f. And the inverse is obtained by interchanging the values of the domain and range. So the domain of the inverse, the domain of f inverse, is the range of f by definition. And the range of f inverse is the domain of f. So we are going to verify that the following pairs of functions are inverses of each other. And we're going to do that by computing the composition of f and g and the composition of g and f. So if one of them is equal to f, the other one will be equal to f as well. The first pair of functions is f of x equal to x cubed minus 4, and g of x equals the cube root of x plus 4. Okay, so we're going to do the composite. We're going to find the composition of F and G. So that is F of G of X and G of X is the cube root of X plus 4. So F of the input is the input raised to the third power minus 4. So this is the input, whatever that is, minus 4. But the input is the cube root of X plus 4. And the cube root cancels with the third power. So that is what? This is X plus 4 minus 4. And that is equal to X. So if one is true, the other one will be true. We're still going to check the composition of G with F at X. This is G of F of X. So that is G. F of X is X cubed minus 4. And G is the cube root of the input, where the input is X cubed minus 4 plus 4. So instead of X, we're going to substitute the whole thing, X cubed minus 4. So negative 4 plus 4 becomes 0. This is the cube root of X to the third power. And the cube root and the third power cancel out. So that is equal to X. So yes, F and G are inverses of each other. Actually, I only have one. I call this number 1, but we only have we only have one example. Now, how to find the equation of the inverse function? This is on page 411. For a one-to-one function, f defined by an equation y equals f of x, we can find the defining equation of the inverse function as follows. Step number 1, interchange x and y. Step number 2, solve for y. And step number 3, replace y with f inverse of x. So that's what we're doing in the next examples. We are finding f inverse of x. Now I have more than one example this time. F of x is 3x minus 8. Okay, step number 1, interchange x and y. So this is the same as y equals 3x minus 8. So step number 1, we're going to interchange x and y. And we're going to solve for x. So to solve for x, you know how this goes. Add a to both sides. Or you can just pass the negative a to the other side with opposite sign. And then divide by 3. So x plus 8 over 3 is equal to y. Or y is x plus 8 over 3. Step number 3, replace y with f inverse. So f inverse of x is 8 is x plus 8 divided by 3. And that's it. So yes, we have the inverse of f. Number 2. F of x is 2x cubed minus 6. So if you want, you can rewrite y equals 2x cubed minus 6. And to find the inverse, we're going to interchange x and y, solve for y, and once we solve for y, we're going to replace y with the inverse of x. Okay, so let's solve for y. So bring the negative 6 to the other side. Divide both sides by 2, or bring the 2 to the left side dividing. And then take the cube root. The cube root of x plus 6 over 2 is equal to y. So the inverse of f is, if f of x is 2x cubed minus 6, f inverse of x is the cube root of x plus 6 over 2. Okay, so we found the inverse of 2x cubed minus 6. Enter the example, same question. We're going to find the inverse of the function. So third function is f of x equals the square root of x minus 4 plus 7, where x, we have a restriction because we have a square root. So we know that x minus 4 cannot be a negative number. So we have the restriction that x is greater than or equal to 4. Or what is the same? This is y is the square root of x minus 4 plus 7. Okay, so there's another observation. Actually, there are two observations. The domain of f is 4 to infinity, and the range of f the range of the square root of x minus 4 is 0 plus 7, so the range of f is going to be 7 to infinity. So the domain of the inverse is going to be 7 to infinity, and the range of the inverse is going to be 4 to infinity. So let's find the inverse, interchange x and y, and solve for y. So that's a y. So subtract 7 from both sides. It's the square root of y minus 4 is x minus 7, then x minus 7 squared is y minus 4. And bring the 4 to the other side with positive sign. X minus 7 squared plus 4 is equal to y. And f inverse of y, or f inverse of x, is x minus 7 squared plus 4. So we know that in general, the domain of x minus 7 squared plus 4 is all real numbers, but we're going to make a restriction. We're going to restrict the domain to make sure that this function is 1-to-1. So the domain of f inverse, just to make sure that the inverse of f inverse is indeed f, the domain is going to be 7 to infinity. we're restricting the domain, and the range, we notice from the vertex, is 4 to infinity. Okay, so let's compare the graphs together. Yeah, so this was the inverse. And that's, of course, when we restrict the domain. So actually, that's inverse. That's not the function, that's the inverse. So let's compare the graphs of the last one. I mean, we can do this for the 3 graphs we did, but I want you to notice something, that the coordinates of the point are going to be switch. Okay, so this is what we're going to do. So we're going to take the x values from 1 through 9. And y values from 1 through 9. Okay, the first function was, or the function f was, the square root of x minus 4 plus 7. So that's, the graph is going to be the graph of the square root function shifted 4 units to the right and 7 units up. So that is going to pass through the point 4, 7 through 5, 8. And the other one is going to be 8, 9. This is the graph of the square root of x minus 4 plus 7. And the coordinates of the points we chose are 4, 7, 5, 8, and 8, 9. And if we restrict the domain, the graph of x minus 7 squared plus 4 is going to be the graph of x squared, shifted 7 units to the right and 4 units up. Or the vertex of that parabola is going to be 7, 4. So this passes through the points 7, 4, then 8, 5, and 9, 8. And at some point, they are going to intersect each other. But you can see from the graph that the coordinates are flipped. And not only that, that's going to be symmetric with respect to the line y equal to x. So this is the line y equals x. The graph is going to be, or you can see that the graph of the inverse is a reflection of the graph of f across the line y equals x. Okay, and the last example is going to be how to find the inverse, or find the equation of the inverse of a rational function. So our function is going to be f of x. I'm writing this, it's going to be f of x. equal to 2x minus 1 over x plus 3. We're going to find the inverse. And we're going to determine the domain and range. So this type of rational function is one-to-one. Okay, so observe first that x cannot be -3. In the last section, we learned that that's where the vertical asymptote is. So the domain of f is going to be -infinity 3 or -infinity -3 union -3 to infinity. Also, y cannot be equal to 0. So there is no x value. Let's see. Okay, just making sure. Oh, yeah, actually, that is going to be equal to 0. So we're going to determine the range later on. Yeah, so forget it. So forget about this for now. We're going to start by finding the inverse. So we're going to let x be 2y minus 1 over x plus 3. And we're going to solve y plus 3. And we're going to solve this for y. So let's solve for y. Let's bring the y plus 3 to the other side multiplying. Okay, so distribute. Now let's solve for y. What do we do here? We can factor we can factor x. Let's see. We're solving for y. So we already distributed that. We're going to write the x on one side and the y's on the other side. So let's bring the 1. Let's bring the 1 to the left, and the opposite of xy to the right. Okay, and now we're going to factor y on the right side. So that's a y. So that's 2 minus x is correct, but this is y. And y is 3x plus 1 over 2 minus x. So that is going to be f inverse. So the other observation is that, well, the horizontal asymptote of this function is 2, and not from the inverse that x cannot be 2. Okay, so now we have the function and its inverse. So that is f inverse of x, and that one was f of x. Okay, so last thing, the domain and range. The domain of f is equal to the range of f inverse. This is -infinity to -3 union -3 to infinity. And the domain of the inverse is the range of the function. Okay, so the domain of F inverse is everything but 2. So that's negative infinity, comma 2, union 2 to infinity. Okay. So with this, we have covered the first section of chapter 4. Thank you for listening.